Homework 2, problem 8. Find the magnetic field everywhere for a circular wire carrying a current density that is proportional to the distance from the center of the wire. So it is equal to Ks, where S is the distance from the center of the wire. In order to do this, we are going to use, since this is such a symmetric system, we're going to use Ampere's law, the integral form of Ampere's law. That is written as the integral around the edge of a surface, dl dot b, 1 over mu naught, is going to be equal to the surface integral, integral d2x n hat dot j of the flux through that surface. In order to do this, we have to figure out what our Amperian loop is. For cylindrically symmetric systems, the usual Amperian loop is simply a hoop that is centered on our cylinder. Because of the right-hand rule, I'm just going to say that our hoop is going to point in this counterclockwise direction, because the current is flowing out of the page in this instance. And we can now start talking about, and so there's the surface, and so we can now start talking about how to simplify this. At the edge of this, we know that dl vector is going to be dl times phi hat. We know through symmetry arguments that the magnetic field is going to be only in a phi hat direction, and it will only depend upon the distance from the center S that we draw our Amperian loop. And so for the left-hand side of this system, again, this is independent of phi, so dl is basically just an integral around phi. So we get the circumference of this loop, which is going to be 2 pi s 1 over mu naught times b phi as a function of s. And that is the left-hand side of the integral form of Ampere's law. On the right-hand side, we actually have to do this in two different regions. If s is less than a, we have to evaluate this integral. And so n hat for us is going to be in the z hat direction in cylindrical coordinates, and our j, here I didn't write it, is also in the z hat direction, right? Because it's coming out of the page along the axis of the cylinder, so that's in the z hat direction. So j is ks z hat. So n hat dot j is simply ks. Also in cylindrical coordinates, this d2x is going to be integral s ds, or really this should be s prime, 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 0 to s, and integral 0 to 2 pi d phi. But again, j is independent of phi, so this can simply be evaluated to 2 pi. So the integral of 0 to s of s prime ds prime of ks is going to be equal to, let's see, k over 2 s squared. And so on the right-hand side, we're going to have k over 2 s squared for s less than a, and k over 2 a squared for s greater than a. Divide both sides here, and we're going to find that the magnetic field function of s is going to be equal to mu naught k s divided by 4 pi for s less than a, and mu naught k a squared over 4 pi s for s greater than a.